Next, in this very track, number 2, we're discussing, again, learning from little and intelligent data management, a problem that we're often facing in the mechanical or in the machine production industry, where we have different machines, different parts, and a lot of factors, but sometimes not a lot of data. And today we will learn how to do predictions in that environment. And I'm very happy to introduce Thomas to you. Thomas is responsible for the project portfolio at Kistler Instruments and at the Kistler Innovation Lab. You have a background in mechanical engineering, very useful probably in the context of your talk today. You also have a master in micro and nano systems engineering and experience in software development as well. So Thomas, without further ado, very much excited to see your presentation.
Thank you very much. So welcome from my side to that talk, Quality Predictions in Metal Machining. As a project manager, I have the honor to be here today as a representative of the whole team, which I want to thank you on that situation here. So let's have a look what I'm going to talk about. Quick introduction to the Kistler Innovation Lab. Afterwards, we are going to have a deep dive into the journey of the project itself, starting from the business understanding and basically going through the whole story to modeling and evaluation of the results. And by the very end, I want to give some key takeaways, mainly from a business point of view, so towards data-driven services. Kistler has actually quite an evolution behind already, starting in 1959 as a component supplier, so pure sensors and not much more into the whole measuring chain. This lasted for a couple of years, but in the last 20 years there were several transitions taking place. By 2004, the company made the transition from a component to a system supplier, which was enabled by introducing several powerful platforms, such as an embedded platform and software corresponding to it. The next step was the step to a solution provider. So this was basically the step towards IoT business and cloud business. The just recently taken transformation finally ended up in the provider for the information itself, so database services, mainly, and also our digitalization topics were touched in that transition. And exactly by that time, the creation of the Innovation Lab was done in order to push those digitalization steps exactly into the way of data science. Turning data into value. That's basically the vision behind the Kistler Innovation Lab. We want to unveil this full potential of the data by combining sensor technology, where we are strong from the history, including domain knowledge and data science. Kistler started in very small niches, expanded to other niches, but also expanded in more and more applications around those niches. What was missing so far was the data science part, or actually it was just done within our conceptions, but not focused. And this is one thing which was really introduced by the Kistler Innovation Lab. What is unique about Kistler is also that we have experts in every field, such as the tech side. We have a strong technology stack, starting from the sensor to the data acquisition systems, data management systems, but also analytics. But also we are in so various applications, so we have a broad field of expertise in the domain know-how, which is key to success for most of our projects. Obviously, we have a strong business support as well. All in all, the shared strategy and goal is the key to the success. And the project which I'm going to deep dive now is luckily located in Kistler itself. We actually had a customer in the production of our own sensor production. So the domain business was strongly pushed from that side, and we had easy access, which is not always the situation in such data science projects. The tech side was mainly driven by the Innovation Lab, but also supported by several other departments. Finally, the business side, it is covered by a focused business unit called Advanced Manufacturing, which serves exactly such situations with sensors and data acquisition systems, or even complete solutions. Okay, so let's dive into the project. As a start, I want to quickly show you a video which is explaining quite well the whole situation and setup.
The production of very thin-walled and small workpieces with wall thickness of only 0.035 millimeters is our specialty. They are usually made of high alloy steel or superalloys. The production of these parts can only be realized with precise computerized machines. Our mechanics' core task is the manual production of highly precise tools and the setup and programming of the CNC machines. Setting up and tuning the machines can take up to 5 hours. By contrast, completing a workpiece only takes about 2 minutes. Most of our workpieces have a diameter of 0.3 to 10 millimeters. The smallest drillings that can be completed true to size are 0.2 millimeters. Already, the smallest force effects can cause deformations and make a workpiece unusable. Our workpieces are continuously monitored during the production process. We only allow deviations of a few micrometers, which are invisible to the eye. The slotted spring pin as well as the membrane are the centerpieces of our sensors.
What did we see in that video? Actually, I want to point on some things. So the first thing is, this is actually the piece of metal which we are going to produce. So it's really small, and the maximum dimension is just a little bit around 1 centimeter. So obviously, such high precision tooling is only achieved by high precision turning lathes, so the machine itself. On this side, you can see several drillers, but also cutting instruments, and the whole machine is obviously completely automatized. Now, coming to the process in a more detailed way, the whole process to produce such a piece is a sequence of process steps. So starting by the raw material feed, there's first roughing and drilling situations, but then there's fine-tuning, surface machining, and finally it's parting off, and then the quality check applies. So the challenge is exactly behind those points. We have several process steps before we even have the part finished, so that means in every process step something can go wrong. On the other hand side, quality is actually checked just subsequent. So whenever we start producing a part, again, we are just in the same time having the quality check. So in worst case, we are about to lose up to 3 or 5 parts if the quality was bad. And the last thing is also, to the same reason, the manual machine parameter corrections. So they are actually done preventive or subsequent, since we are relying on the quality measurements there. So what is our goals? The goals was the prediction of the part quality already during the processing. On the other hand side, and this is one very important thing for the production itself and the development of such sensors, where is the process step which is the most fragile, which is causing an issue for the quality. In order to do so, we have to measure and analyze process parameters. So what is our process parameter in that case? The most relevant I want to introduce here. Think of a situation in your kitchen. You're taking your old knife, have a nice tomato, and you're going to cut it. You will get a result, but it's not very nice. So maybe you take a sharp knife, and it's going through the whole tomato like butter. Quality is good. And that one shows quite intuitively why cutting force, the force applied by cutting, is really an excellent parameter to characterize not only the quality, but also the tool itself. And that's what we are going to use. So look at that one. This is basically the time since the part production starts, from left to right, so the whole sequence. And on that side, we have the cutting force. Don't look at the numbers, only look at the amplitudes. In the very first one, there is quite characteristic strong amplitudes coming in. There's a whole lot of material taken away. Then there's the drilling process, so a different tool, which has high frequency stuff inside, for example. And then there is several minor situations in terms of amplitude, but very, very important steps which have clear characteristics for each individual process step for fine-tuning, or let's say, fine machining. But at the very end, amplitude gets bigger again. That's when the part is going to be parted off and finalized. So what we can do is here actually take comparisons within such a process steps or also across multiple process steps. And here I want to quickly introduce how we did the data-driven approach. So as an input, we had the cutting force, but you also took the machine data next to it. And finally, we get some labeling out of quality logs. But they are actually just a list of sequential list of findings corresponding to the parts. So we leave the shop floor and go now out into the cloud environment where we introduce a structured database for the analysis, which is the base for the extraction of features, serving a machine learning model, and finally giving back to the shop floor the results in terms of insights or reports. So now we dive exactly into that one. Let's start with data preparation. So in here, already the business understanding was very challenging from the very beginning, and we invested a lot of time on that one. This is due to the fact that we first of all had to understand where did such a part processing really start, when did it stop? And we had manual interruptions, several of them. We have manual interruptions just because the operator is doing something else in order to prepare a next sequence of steps. Or it's actually also just maybe stretched the whole process in terms of timing. So as an input, again, we had even unstructured data, continuous data, but also discrete data. They were not nicely matched. Quality log, I did already say, it's just a list. So what we use is a combination of the method called matrix profile and dynamic time warping to identify such windows of interest. On the right-hand side, you see, for example, in here, that might be the reference pattern, and output of the matrix profile for a perfect fit would be 0. Then on the right-hand side, we identify start and stop sequences when the pattern is very, very similar to a reference. Finally, by that approach, we achieved a database for process data per part, all combined, and with quality labels together. Now I want to get a little closer to the feature engineering, which is, again, very strongly driven by the domain know-how as well. But for that approach, we also introduced generic features, obviously minimum, maximum, average. And I want to point out 2 more, the Euclidean distance to average, which actually is looking to the distance to an average on a certain sample time. But also, again, the dynamic time warping, which is taking into account the time-shifted situations in between a reference signal and a signal under observation. So we have that feature table. We have a lot of insights inside there. So let's have a look at the evaluation. Once again, the turning lathe is a highly engineered machine. So process should in generally be robust. But the cutting force is also an excellent parameter to have these deep insights into the process. So as a visualization in here, one can already see on the left side a robust process. This is the red one, is the average curve, an average pattern. And around we have several single measurements of single parts. And there is the deviation, as usual. But they are actually following that signal quite well. A fragile process. This one, for example, shows a lot of deviation in the very end. And effects like that we are taking into account. So we had the first goal, the quality prediction during the process. So once again, quality issues are very likely if we at least have one of the process steps in the machine which is not performed correctly. That one is actually differing for our expected stuff. What we used is a machine learning model, XGBoost, for the classification. And as usual, in production, everything is optimized. We did not have too much bad parts. So we used also a class handling method, SMOTE, synthetic minority oversampling technique. The model performance we can give here is actually to identify the good parts was quite good, the precision, around 96%. So what we get out of that one? We can say quite good, okay, this part was a good one. We can directly put it to the green bucket. On the other hand side, if we see that it's not clear that it is a good one, we can bring it back to the quality inspection for a closer look and putting it into the right basket. So the other goal, the fragile process steps. For that goal, we introduced an error score. This is actually an indicator where to optimize the process. On the left-hand side here, you can see an example for a bad quality part with, again, all these process steps in the whole sequence. And with a high error score, it's indicating for this example, the whole finishing, that process in here, was mostly affecting the bad quality, or let's say the error source. Obviously, there are some more, but there is a clear indication where to start in further investigation. So let's come to the key takeaways out of the project. Our production is currently acting in a preventive way. So optimization is actually done by limitation of number of parts per tool in order to actually avoid bad quality. What we are currently working on is in-production control by introducing feedback loop exactly on the cutting force itself, but also introducing automatic sorting of the good parts and quality bad parts. Take a look into the future. We have the predictive part. So we will be, hopefully, ready to plan and optimize the tool lifetimes, or also observe other stuff by cutting force monitoring. How could such a solution look like? By introducing such sensors into the whole machines and to the tools, we can prevent machine damage and waste. We can monitor trends in individual process steps, but also predict and optimize tool usage lifetime. And finally, this one is quite a good summary of what you just heard, but it's also what is our way of working. First contact is usually done by a Kistler expert, somewhere in the sales team. Subsequent workshops to really frame all together in the triangle of knowledge that problem and discuss the feasibility. Out of that one, a setup is introduced for data acquisition, and on that one, we introduce also the analytics part, mainly driven by the innovation lab. And finally, we're going to design a clear deployment for our customers' infrastructure. So basically, Kistler is very present here today. I would like to ask you to just reach out to us. On the left-hand side, it's the innovation lab team in here, and on the right-hand side, we have representatives from service, from data engineering, and also digital solutions business And I want to quickly point out on another interesting talk of my colleague, cavity pressure-based machine learning services for advanced injection molding processes. Also refer to our website, also for further contact. Yes, and that's basically it. Thank you very much.
Dear Thomas, thanks a lot for your inspiring talk. I learned, for me, cutting tomato is never going to be the same again. And what difference you can make, even for the smallest piece of parts. And with that, I would like to open the floor for questions that the audience might have in person or online via the chat. Any questions? Georg, online? Then I might have one. What's the key advantage that you would like your customers to take away from your approach? Is it, in the end, saving material? Is it sustainability? Is it no bad parts on the consumer side?
Basically, the output is always the same. It's efficiency gain, it's optimization of production, but it's actually more that you have a chance to introduce measures to very complex processes in your production, which you can monitor, where you can take a lot of insights out of it, which are actually not really visible just by following a process which is so fast and you don't have a chance to have a look at it. So one more time, I mean, when such a part is produced, one process step is actually following each other, and you will not see the intermediate results. That's not possible. You can't measure it.
And you've given the example from the turning lathe. Do you see other machines next? And if yes, do we see CNC or other machines where you see similar approaches possible? What's your next step?
The title is Quality Prediction in Metal Machining, so it's applicable to every metal machining process. And we have different systems from Kistler's side, supporting with different designs of sensors, all the different machineries.
Okay.
So that's
generic.
Yeah.
A question here. Please go to the microphone, yes, so the online audience can hear too.
So at the end, your solution, will it be a plug-and-play solution, or do you have to do some calibration before for each part or each machine?
So basically, there's always an interaction with the process owners and developers to introduce a new process. And that's the same with such a method as well. When you introduce a new process on a machine, you have to learn it in terms of having some trials, experiments in the very first round, and then come into optimization. So I see it as a step-by-step approach. Usually, the first thing is you have your algorithms working next to the production. It's still manually controlled. Then it's taking over more and more, like you're already sorting into the correct buckets. But sometimes somebody's really still overlooking the process. And then finally, once the whole process is really robust, you can automatize it completely.
But that's the talk next year then.
Definitely.
Any more questions, Georg, from online? Okay. Then, Thomas, thank you very much. A small gift for you, and I have a second one for Nikola.
Just here.
Thank you
very much.
Then, thank you very much for your presentation once again.